Hey guys, welcome back to my channel. Good evening. Um, Today I promised that I was gonna go through an example of um, the graphs, right? So I tried solving a question. It was medium level difficulty, so it was pretty difficult, but it also had all the essentials that we have talked about. Let me just share the screen with you. Yeah, so basically it's Leetcode 547, number of provinces. There are n cities, some of them are connected, some are not. If the city A is connected directly with city B, and the city B is connected directly with city C, then city A is connected indirectly with city C. So if you put it into a numeric form, then is connected, bracket I, bracket J is one if the ith city and jth city are directly connected. So yesterday we talked about being undirected and directed, right? So um, directed means that the edges, you can go back to its uh, no, sorry. No, sorry, it's a different case. I was thinking about the binary trees and the undirected cases where uh, a children node cannot go back to its parents node. But this is a different case, right? Because it means that it's connected and some components are not connected. So it's basically counting the number of connected components. Um, so, like as you can see from example one, there are two connected components. One and two is connected, three is not, so there's two. So output is two. In example two, you can see that um, there are three connected components. They're not linked together, so this makes sense. Um, what else? What else has to be noted before solving this question? Hmm. Yeah, it's a different type of input form, right? It's one of the input forms that we looked at yesterday. It's in an adjacency matrix, so there's I and J, and it's adjacent. Um, we we mentioned briefly that unlike adjacency list, if it's adjacency matrix, then it might be better to use a hash set to prevent ourselves from going through all the nodes that we have visited. So we are also going to use a set in this problem to specify a set of scene, so a set of nodes that we have already visited, so we don't have to visit them again. Um, we can also treat each of the cities as n, so nodes, with each city labeled from 0 to n minus 1. And um, let's actually put this into things that we need. So before we start traversal, we have to first build a graph so that we can easily access the node's neighbors. So this is like a standard first step for solving any graph problems. So it's just building graphs. And it should be similar in the way of building this graph across all the problems. It's just like the template that we have used for sliding windows or um, building hash sets where uh, you were supposed to build empty dictionary. Um, what else was there? DFS, BFS, where you have to specify node left and node right using recursion. Uh, BFS, where you do it iteratively. So it's also part of the template. What I want to say is this is part of the template. So we have to first build a graph. Building the graph. So we iterate over all pair of cities, um, I and j, and if is connected, what was this? Is connected, I, j is 1, then we can add an undirected edge between I and j. Add undirected edge. Yeah, right. Okay. And now we have to, what do we have to do after building a graph? We have to count the actual provinces. So for provinces, we can start at any city in within these nodes, and you can find a path to reach any other city. And this means that they form a connected component. So that so province is defined as connected component. In other words, connected component where you can start at any city. And we use depth first search. So finding provinces, use depth first search. We use depth first search to traverse through the graph. And traversal starting from any node will visit all nodes in its connected component because they are obviously all connected together. So this makes sense. So probably there's going to be some recursion as well. Now we have to actually implement recursion, right? So we have to implement TFS. And with, like I said, for adjacency matrix, there's most of the time there should be a case there where we have to specify a set of scene, um, which we have visited, the nodes we have visited before. So in this case, we use it to keep track of the visited cities. So for each city, if it has not been visited before, then we perform a DFS starting from that city. And during the DFS, we mark each city uh, in scene, so we append it, and then recursively visit its neighbors. So, uh, hash map. Now, what's last? We've built a graph, we've found the province, we implement DFS. Also, we have to now do what we were originally asked to do, which is counting provinces. So we iterate over all the provinces. And if the city has not been visited, then we initiate a DFS marking all cities. Um, and after each complete DFS traversal, we increment the province count in some kind of variable that we have already specified. And um, it ensures that each province is only counted once. Yeah, so this is basically the core structure of how we're going to do this. Um, and frankly, I haven't solved this myself. So it is not my original solution, um, just for a disclaimer, but I've tried myself to implement it. Okay, so now let's try to implement it in a code. So we have to build first a graph, right? So in order to do that, we have to count the number, I mean the length of the matrix, the adjacency matrix. So in this case, it's given like this. So I guess it takes time to get used to this kind of input, yeah? List in a list uh, in a Python context, of course. So n is the length and a length of is connected, and now the graph is default dict of this list. Yeah. Now, for I in range n, we're starting from 0 to n minus 1 node, right? So that will be for j in range I plus 1 n. We're traversing through all the nodes in the is connected adjacency matrix. And now if it's an if the is connected ij is 1, then means that we have to add an undirected edge. So is connected ij, we did this yesterday, right? Now we're gonna, if it's a directed edge, we would have only appended j, and because we have to add undirected edges, we have to add to j as well. And now we have built the graph. So for instance, if there's like a graph of label 3 or 4, then it will give some kind of list inside a list. So yeah. Now that we have built the graph, what's the next step? We have to find provinces, and we have to set a core DFS algorithm that we are gonna utilize. Now, how are we gonna do that? We use the recursive DFS function, so that will be DFS node, and for neighbor in graph node, graph with the label node, and if this neighbor is not visited before, so how are we gonna do this? We are gonna assume that we have already defined the set scene, not in scene. We're gonna define it right afterward. We add it to that set, and DFS, we do the function call, right? So yeah. Okay. We make sure that scene is a set. And now, what's the last step? We have to actually count the provinces. So for I in range n, n is the length of the input adjacency matrix. So in this case, it will be 3. If I not in scene, so if that number is not something that not the node that we have visited before, then we define some kind of variable. We're going to do that as answer equals 0. We count the provinces. And at the same time, we add to the set of scene to make sure that we don't visit this node again. Or if we visit it, we know that it's a node that we have visited before. Then we do the first search from that node because we have not visited. Right? And then we return the answer. And let's see, Nativor. Oh, nice, it worked. But as you can see, it's very, very. Oh no, actually, it's no run time complexity wise, it's n squared, so it beats 86% of the solution. But space complexity wise, it's constant. So um, it's actually very behind most of the solution. Shall we see what other solutions are there quickly? Python. Yeah, so this person also constructed a graph. Each person has a node, edge between two nodes. Wow, so uh, we have read all the values in the matrix, but for this person, he only read half of them because the matrix is symmetric. I didn't really think of that. So he built a graph here, and I don't know where he specified the symmetry. This one undirected graph. So until here is same. I guess it's this line that uh, it shows. So he's only reading the false. So it's only half. Okay. Time complexity O(n) square. O(n) square for the worst case. Well, anyways, it's almost the same. Um, so I guess when we go through all the algorithms, I think the best way is to memorize the templates. So for this kind of case, adjacency matrix case, uh, building graph for starters, and uh, if it's undirected, adding undirected edges. I think it's very crucial. And building a hash map um, and using a scene set and sometimes using DFS, sometimes using BFS. I guess it doesn't matter, but uh, yeah, these kind of crucial templates, I think it's worthwhile to remember them. But anyways, that was it for today, guys. It was a very difficult question. I took a bit of time on it, and I still couldn't solve it. Tomorrow, I believe we're gonna move on to BFS in graphs, and if we have time, we'll also try to solve some question as well. Or maybe we'll look at other input types for um, DFS in a graph, but we shall see tomorrow. Thank you guys all for listening. And if you guys have any comments, leave it below.